to go back to what we were discussing, we said that what was very important if you want to compute combustion instabilities was to know the boundary conditions at the inlet and the outlet of your combustion chamber, here and here. So that really means that when you do CFD for combustion instabilities, right away, you need to forget what you were doing before. You cannot say, I'm imposing the velocity and the pressure. You have to describe things also in terms of impedances at the inlet and at the outlet, because they will change the results. So the impedances in a real gas turbine, of course, are difficult to specify, because they depend on what's going on both sides. There are a few cases where I've already shown you that. The wall, the impedance is infinite. The atmosphere, the impedance is 0. The case where there is no reflection, the impedance is equal to rho C. And then there's one case which is of interest. It's the case where you have a choked nozzle at the outlet. If you have a choked nozzle, there's a theory by Marble and Candle again, where you can actually see that it's almost as if you would have U prime equals 0 at the outlet. So it's almost as if, okay? So in a simulation, you can use that as a boundary condition. The choked inlet nozzle I've shown you already. This is a table which summarizes the values of impedances in a few simple cases. So choked nozzle at the inlet, where the flow rate is imposed, it's 1 minus 1 over m for the impedance, which is normalized by rho C here. And you can see the different values here, depending on which kind of flow you're doing. This is what you need to impose. And actually, if you go to most codes, they don't even care about impedances. Okay, so you take a Fluent or Converge, impedance is not, it's not even in their language. So you have to worry about that. If you want to do instabilities, you need to know. So in the other cases where it's not a simple one, the impedance at the inlet and at the outlet are unknown and something you need to find. And these are not simple quantities. This is an example here of a measurement of an impedance in a system here which has a multi-perforated plate. You can measure the impedance by sending acoustic wave and measuring what's coming back. And when you do that, you have this kind of function. It's a function which is a complex number, so it has a modulus and a phase, and it depends on frequency. And it can depend on frequency in various ways. And depending on what you do here, you will have a different unstable mode. So we need to account for that. Every time we talk about LES of something, we need to account for that. In other words, you cannot talk about the instabilities of this chamber. That doesn't mean anything. It's the instabilities of this chamber plus a set of inlet and outlet boundary conditions. If you don't specify that, it doesn't make sense. That also explains that if in an engine, a chamber is unstable, you take it off the engine, you bring it to IITK, put it on a bench, it doesn't have to be unstable anymore, and vice versa, because the impedances are not the same. So that's a big problem, because it really tells you that if you don't include impedances in the way you understand things, you're not going to do it. So,
how will you include this impedance in LES with the time-domain simulation?
Exactly, you need time-dependent boundary conditions, and that's tricky. Yeah. The other solution is to extend the domain sufficiently far to a place where you know the impedance. Yeah, you will see, for example, for piston engines, what we did, we actually added a big plenum, and we computed up to the plenum so that we could say pressure was imposed. It's another way to do it.
So acoustic equations are hyperbolic in nature. So outlet impedance, how is it measured?
Oh, impedances are independent of turbulence, okay? It's two different worlds. So normally, the impedance you have to find by measurements or by some kind of theory. And in a gas turbine, usually you measure them because it's too complicated. Okay, so now I want to go back to this business of LES. There are two strategies now, if you want to use LES to attack this problem. The first one is what we'll call self-excited LES, and the second one is acoustic codes using also some of the LES. So forget entropy modes for the moment. Okay, this is the loop we want to compute. I won't talk about the entropy modes for the next minutes. So the first method is really you use LES only. You don't use an acoustic code. You are very rich. You have as much CPU as you want. So The problem is to mesh the chamber until you reach a place where you know the impedance, and if they are complex numbers, there's a small detail to implement complex impedances. I don't want to talk about that now, it will be a little bit too complicated. For example, this is the Alstom chamber. We computed far upstream and far downstream, and here, when you do that, the simulation itself will produce an instability. Okay. And it's a product, it's a result of the LES. That's, I would say, the brute force method. The problem with this method is that it's quite expensive. It depends on the impedances. If you get one of them wrong, you will have the wrong mode. And in the best case, it will oscillate, but it will not tell you much about why it's oscillating. It just tell you, okay, it's oscillating like the experiment is oscillating. So it's not probably the most scientific way of looking at the problem. You need it, but you probably need other methods. So the other method is based on acoustic codes, and you know, this famous cut the problems into smaller problems. That's what Wolfgang Polifke is always saying, divide and conquer here. So what we're going to do is going to study the acoustic loop, and the non-acoustic part will do it separately. So this is the idea of the Flame transfer function. This part will solve in an acoustic code, and the other part here, which is providing Q prime as a function of U prime, will be given separately. So what does it mean separately? Well, you can do many things. If you have an acoustic solver, you need to specify impedances, sound speed, and flame transfer functions. So that's easy. The sound speed is the temperature and the composition. So you can specify it using a once computation, for example. You take the mean sound speed field, and that's the input for the acoustic code. The impedances, more tricky. If you can stop at places where you know the impedance, it's simple. And so the flame transfer function is the main problem. How do you get it? Well, for the Rieke tube, that's the expression we used, and there are more complicated expressions for the flame transfer function. This expression is in the linear world. It says that the response does not depend on the amplitude of forcing. We know that actually it does, so today there are people using what we call the flame describing function, which is a function where the two numbers here, n and tau, depend on frequency and amplitude. But for the moment, we'll stay in the linear regime, so we still use the flame transfer function. So flame transfer functions can be measured or computed. Okay. In both cases, what we're going to do, we're going to send an acoustic wave to the system, and we're going to measure the global heat release. That's a rather simple methodology. Experimentally, you can do it, and you can do it with LES code. So this is a picture I've already shown. So this is a Bunsen flame, for example, where we pulse the inlet with a given signal, and we look at the response. Those are two harmonic signals. You take any FFT method, and you will find the modulus and the phase of the transfer function between the two, so you will have n and tau. And all the physics, all the chemistry, everything linked to fluid mechanics, everything not linked to acoustics is going to be buried in this n and tau. Same thing here. That's what we did for Siemens, for example. That's a Siemens burner. We pulse the inlet, and we measure the reaction rate, so that's what it gives. You can see here the flame surface when you pulse it, so you can see how strongly this flame reacts to forcing. And here you have the total heat release in the box, in the burner, and here you have the inlet signal. So with these two things, you can back up the flame transfer function.
So how do we decide upon the kind of signal to be sent to the inlet?
Oh, usually you have many things. You can use a sinusoidal wave. You can use many sinusoidal waves at the same time if you want to save money. You can use an impulse function, or you can use white noise, and then you use Wiener-Hopf methodologies to extract the flame transfer function. But the principle is always the same. You just get the answer from a forced simulation when you inject the forcing. The problem is that you can do that only if the flame... Oh, sorry, question? No?
If you decide send, you can put multiple frequencies as forcing frequencies.
Yeah.
How you decide upon the magnitude, amplitude of the forcing?
Yeah, exactly. That's the problem. You can do it with many frequencies if they don't interact. But in a turbulent flow, you need to use some, high level of forcing, because otherwise it's lost in the turbulent noise. So in turbulent cases, usually we use only one frequency at a time, which is expensive, because if you need to do 5 frequencies, then you need to wait, you need 5 computations, and that costs. So there's another problem also, is that you can force only a flame which is stable. This flame, for example, is already unstable, so you're not going to add a forcing on something which is already unstable. It's going to be a mess. So it's the same thing for this flame you have seen before. If this flame is already oscillating, you cannot add an oscillation on that. It will be too complicated. So the solution there is that you need to cut this loop here. If you can cut the loop, then you can make this system stable, and then you can measure the flame transfer function. So what do you mean by cut the loop? Well, in an experiment, one way to do that is to get the flame out of the box. Okay? If you remove the flame from the chamber, the acoustic coupling will disappear because the flame will be a free flame. That's one solution. In LES, one way to do that is to change the boundary conditions acoustically. So either you change the flame position or you change the flame itself also. What you can do is change a little bit the occurrence ratio to go to a stable case. There you measure the flame transfer function. In both cases, here you change the geometry, here you change the operating point. There's not much choice. I mean, if you want to measure an FFT, you have to do that. Now, another problem, I just want to touch that to explain also why I spent so much time yesterday on this question of boundary conditions. Introducing waves is not that simple in a code. You could say, okay, I just have to pulsate the inlet. Well, it is true and it's not. We need to make sure that we can handle all these problems at the same time, the turbulent injection, the mean flow, and on top of that, now we add an acoustic signal. So if you just do it without turbulence for a laminar flame, that's something we did some time ago. And there are two intuitive ways to force an inlet. So suppose I have a boundary condition here, and I want to pulsate this thing. The beginners, or the advanced people, will say, well, that's easy. I just say U equal U plus U prime sine omega t. But that's not a good idea. That's someone who has not learned about an SCBC, you know, because the physics is that in the real world, in the subsonic world, you cannot impose a fluctuating velocity like this. You can send a wave. That's right. You can have a loudspeaker here, sending a wave, which will enter here. But if there is a reflection, this reflection will be added to the incoming signal. You won't be able to have the velocity you want. What you really want is to introduce an acoustic wave. And I'm going to show you the difference between these two cases. When you do that, imposing a velocity that you control is actually fully reflecting for the waves that you don't control. If a wave wants to come back here, at this point it will meet a point where velocity is imposed. It may be variable with time, but it's imposed. So the wave will completely reflect. And if you force here and don't let it be non-reflecting, then the system can start oscillating and do something which is not what you want.
So in this, the philosophy is, I mean, we actually cut the feedback loop from the acoustic, right? So
Yeah, the feedback loop is gone here.
yeah, so basically, like if I do an experiment, I mean, somewhere in the downstream, I have to put something so that I can simply observe all the acoustic waves.
For example, yeah.
So that if I do that in the numerical simulations also, then there will be no information which is going to go down.
Okay, in that case, we don't change the geometry. I'm going to show you an example. In that case, if we do this method here, we don't have to change the geometry. So we can stick the same geometry, we just make the boundary conditions different. We make them non-reflecting. Let me give you an example. So we take this case, okay? That's a simple one. That would be the same as the experiment. That's the Bunsen flame. Here you want to introduce waves. So in the experiment, you would put loudspeakers here. Okay? And in the experiment, depends on the case, but if this case is stable, then you will introduce waves, and these waves will shake the flame. That's no problem. If you do the same thing now in the simulation, you will replace the loudspeaker by a forcing here. So either you write U equal U0 plus a simulation plus a perturbation, or you write a wave. In other words, you say that now I'm not going to impose the velocity, I'm going to impose the wave which is coming in. So I'm going to say that there's a wave F here which I can impose. Why? Because it's coming from the outside. The wave which is coming from the inside I cannot impose. It's going to be whatever reflected wave has to be there. And so this method is based on an SCBC, and if you do that, as you will see in a second, it works much better. So let me just show you the comparison. Here, this is the case where you impose the inlet velocity. So you just say U at the inlet is equal to whatever I want. And if you let this thing go, you will see that the wave starts going in, but then some acoustics go back and start interacting with the inlet. This is the inlet velocity. And so the flame starts shaking more and more. And it gets actually self-excited here to something that you don't want until finally it just blows up. The reason for that is that the tube between here and here is not able to evacuate its energy because you have closed the inlet. If you do the same thing with NSCBC, you will see the movie I've shown you before. You have some forcing, but then if noise is generated here, this way it's going out, and this way it's going out too. The fact that it's going out, it's like a train. There are two trains here. One train is entering the domain, one train is leaving the domain. You cannot stop the train leaving the domain. If you impose the velocity, you force the train to stop, then it comes back, and then you have a resonance. So even if you have a code and you want to compute a flame transfer function, you have to be careful about how you do it.
When we do an experiment, the same thing also happens, right?
Yeah, exactly. But in experiments, normally, if you put loudspeakers, you are indeed non-reflecting, because loudspeakers are on the side, so you don't really impose the velocity. A loudspeaker does not really impose the velocity. It adds a forcing. But that depends how you put the loudspeaker. We put the loudspeaker on the side. If you put it like this, facing the tube, then you may have problems. Which, also that means also the amplitude will grow, for example, but in an experiment there will be nonlinear phenomena which will limit the amplitude to whatever you want it to be. So I'm going to probably jump the Rayleigh criterion because this is going to be too complicated for the moment, and go to these tools. So, which tools you need if you want to do some more acoustics? The first tool I think we need to mention is what I'll call analytical tools. That actually Professor Kuchari did that yesterday. You don't even need any code. You can say, okay, this is a combustion chamber. It's mostly walls. There's a small hole here, but mainly it's a wall. So probably the boundary condition here is not far from U prime equals 0. And here at the outlet, if I am releasing this thing into the atmosphere, the boundary condition is probably not far from P prime equals 0. So what is the mode? The first mode which can fit here. It's a mode which has a velocity node, which is a pressure entire node here, and a pressure node at the outlet. So it's a node which has to look like this. Zero pressure here, maximum pressure here. You see that the wavelength of this mode is equal to 4 times the length which is here. That's what we call the famous quarter wave mode. So if you know that lambda equal to 4L, you just have to plug here what lambda is. Lambda is C over F. Then you get F. So for example, for a combustion chamber of the order of half a meter with burn gases in there at 600 meters per second, you find the frequency for the first quarter wave mode of the order of 300 Hertz. Okay? So that's what we call back of the envelope computation. Now, in practice, that never works. Okay? It's a very rough approximation of what's going on because you're simplifying these things too much. So if you want to be serious about it, you should use a code to do that. That's one of these acoustic codes. Acoustic codes, we will freeze the flow. That really means we suppose that the Mach number is not very large. And in most cases, it's not bad. I mean, most Mach numbers in chambers don't go beyond 0.2. So the correction of the Mach number on the acoustic modes is in Mach square. So if you have a 0.2 Mach number in the flow, that's a 4% error on the frequency. That's okay. We can live with that. Now, the world of acoustic modes is split in two. Actually, we talked about it this morning. That's the easy world here is what we call longitudinal modes. Those are modes where waves propagate this way. And the not so easy mode are here in higher in frequency. Those are modes which depend on transverse directions, and then it's a mess because there are much more modes and they are higher frequency and they are much more also. So in gas turbines, Well, actually, we still have these things, but these modes will be found between 50 and 500 hertz. If you go beyond 1000 hertz, you start seeing transverse modes. For computation, this is, of course, much easier than that one because this is really one-dimensional. So here, there's no reason to get a complicated code. You can do it with one-dimensional network code, which I will describe later. So this 1D code, the principle of them is to cut the whole gas turbine in small elements and assume that each element can be described by a small acoustic element. These codes are available everywhere. Alstom has one, Siemens has one, they use that all the time. A Siemens gas turbine, when they discretize it like this, you have thousands of small elements like this for the whole system, and they assemble all of them. So how do you assemble them? Well, you say that the pressure from here to there depends only on two waves, the wave going right and the wave going left. So that pressure can be written like this and velocity like that. We've said that many times. There is no flame for the moment. It's either fresh or burned gases. You write here these two waves, you obtain U prime and P prime, and you can especially now say that U prime is going to be a harmonic signal with U hat and P hat. You plug it here, and you find that at x equals 0, U is A plus minus A minus, and P is P A plus plus A minus. And here, at x equals L, you have the same thing, but now you have exponential IKL, exponential minus IKL. So what you can do now is eliminate these two waves, A plus and A minus, to end up with this system, which tells you that if you have a piece here of duct, the pressure and the velocity fluctuations at the outlet, the acoustic pressure, are just equal to the pressure and the velocity at the inlet multiplied by what we call a matrix. Okay? Very simple matrix, cos KL, sin KL, it's a complex number here. And you can do that for the neighboring point, and you can then assemble all of them. The only question now is to know how you're going to write jump condition from one duct to the next one. So if you look at most of these codes, they just discretize everything here according to this rule. Every time an element is discretized, you give it sound speed. That gives you a matrix. The only problem is how do you assemble them? Well, you have to write jump conditions. Jump conditions, at two tubes like that, you express the continuity of pressure, and you express the continuity of the volume flow rate. That gives you a way to stick these two things together. And there is one special case, of course, is if you, at some point you need a flame somewhere. If you have a flame somewhere, you can derive the jump conditions, and basically they're going to say that SU, the product of surface, cross surface by velocity, is changing because of the unsteady heat release. And the unsteady heat release you're going to model with the entire model. And so when you do that, you end up with a system where the whole engine is discretized by small elements, and you can even actually do what we call 1.5D. That means you can have a 1D network here, but also connect it to another one. For an annular chamber, this is convenient. But all of that ends up in a big matrix system that you can invert very easily. So for example, if you have a system like this, where you have an annular chamber with 6 burners, in 1.5D, it will look like this, okay? The plenum, the chamber, and the burners. It's just square ducts because it's only 1D. But you can do very complicated geometries with this 1.5D system. And here, when you're going to compute the frequency, it's going to be much better than the back of the envelope computation. For example, here, you see the structure of the first azimuthal mode with this description, and it's a very cheap computation. You can write the code like this easily. So, if you want to write a 1D code like this, you need to know the length and the section of each tube, the sound speed. At some point, you need an impedance somewhere, and you need the transfer functions of the flames. Now, in some cases, that's not enough. If you want to look at transverse modes, you need a 3D tool. 3D tools, it's easy, more or less. You take the Navier-Stokes equations. You say Mach equals 0 to begin with. You say it's an harmonic function. Everything is a harmonic function of time. You plug it here, and you end up with an equation which looks like this. You know, all the terms, all the ddt become j omega, because you suppose that everything is exponential j omega t. And then you end up with a big linear system that you need to invert, and it's an eigenvalue problem for omega. So one example, this is a burner where you have cold gases here, burn gases here, and you mesh it like this. You don't need a lot of mesh points because most of the activity in acoustics has a long wavelength. So the mesh you need to do that is much coarser than to do LES. Anyway, remember what I said, everything complicated, chemistry and convection, everything is gone in the transfer function anyway. So you don't need to worry about it. So this is what you obtain, for example, with the 3D code now. So this is the longitudinal modulus of pressure. So here you have a pressure node, pressure antinode. And here you have, for example, the 1L, 1T mode. So it's a mode, when we say 1L, it means it's a longitudinal mode combined with a 1T mode, which is the first transverse mode. And you see that these things start to be more complicated. You see also that, of course, this one is higher frequency than that one. Now, that seems easy, but imagine now you do this guy. So again, this is a Siemens system, and you start computing the modes of that guy, where you mesh everything, and then you start looking at the modes. And the problem now is that between 0 and 300 hertz, you get 40 modes. You get one mode every 5 hertz. And so I've plotted here a few of these modes. You see the structure, that's the plenum, and here you have the chamber. You have the maximum of pressure here. And you see here that here you have the argument, here you have the modulus. That's one mode at 184 hertz. But if you start looking at the other modes, 165, 189, 190, 192, 203, 207. So if you look at modes which are very close, like for example this one 190 and this one 192, they have nothing in common. This one is a transverse mode here in the plenum, and this one is much lower here, but it's a transverse mode in the chamber. And so you see that when we try to do it backwards, if I don't show you these plots, and I just tell you I measured 194 hertz, you cannot tell me which mode it is. The mode identification cannot be done only on the basis of frequency. You need more information. You need, for example, additional sensors which can tell you, which mode you are really targeting, and that's without combustion. Then when you start the flame, these modes move, and you have to track them. This is why it's difficult to make a turbine like that stable. Okay, I'm done with this part, and I plan to move now to examples. Is there any question on that part? Nope.
So, we are trying to simulate instability using LES. Like Ralph told that here gets dissipated, which is not there in LES.
Yeah.
So, what other things I should be careful about when I'm doing simulation of thermocouple instability in LES?
Well, that's exactly what we discussed yesterday. I think you need a code which does not dissipate energy. A code which can convect vortices correctly.
Yeah.
Otherwise, you won't have anything. Huh?
And if you are having a boundary condition which is not varying with time, as you know, so is it possible to use that, or I should have?
If you have what on the boundary condition?
Like you told that ideally your boundary condition should be varying with time.
Yeah. But we fix this problem. That's what I'm going to show now. We fix this problem in a different way. We know that we have to be very careful about boundary conditions. So we just remove them. We mesh the atmosphere. That's how we do it in AVBP. So in this zone here, there is no boundary condition. The boundary condition is far away, and in this way, there's no problem. Every time you compute these things, it's better to be far away for the boundary condition, so you are sure that you do the right thing at the outlet. That's an easy way. Okay, so let me show you. I won't finish that because that's a big part. This is a collection of examples taken from the life of Surfax over the last 10 years. So I don't know how many unstable burners we have studied, but at least 50 now. And so those are just examples of what's going on when you try to fix this kind of problems. The first thing to say is that instabilities, when people come to us with an instability, usually their diagnostic is really strange. We had this case last year. The chamber makes noise when it's raining. That's one of the cases. The chamber burns, or it melts, or it quenches, or it vibrates. And of course, no one knows what's going on, but everyone has an ID. That's usual too. And you have to fix it tomorrow. Okay? And that's actually it's a big problem for commercial instabilities because it's difficult to explain to people that they should have looked at the problem 5 years before. Not now. Because now it's a little bit late, but still they want you to do something. I want to open also a parenthesis. I almost started discussing that yesterday with Professor Kouchari. If something vibrates in a chamber at 600 Hertz, you can always divide the length by speed and find the right frequency. It's not a proof of anything. There's so many things in a chamber which have the same characteristic time, because that's all you're saying, okay? 600 Hertz is the inverse of a characteristic time. So you should not really rely on, I've found that by dividing the diameter of the chamber by the sound speed in the plenum and multiplying by 2 because it's a square chamber, then I find 600 Hertz. No, it's not going to work, okay? If you want to do a serious job, you need to use serious tools here. So another comment about noise. Commercial instabilities make noise. Sometimes you can also have noise without commercial instabilities. In most cases, the spectra show that you have a combination of both. You have combustion noise, broadband, due to turbulence, and you have peaks. These peaks can be small if you have no instability, but then they become big if you have an instability, and it's a continuous process. So you can't really say that there's a world of stable flames with only noise and flames with, instabilities. They go together. I've told you already that instabilities are different depending on the impedances. So clearly in the lab and in the real engine, you're going to have to care about the boundary conditions. So I've said that already. Let me jump now to a few examples. I will begin with the two solvers we're going to use. So I'm going to use the 3D solver for acoustics, which is called AVSP. So as I said, we freeze the flow, we solve the Linear-Helmholtz equation, we take into account the same geometry. The mean temperature field is actually provided by LES. We use the mean temperature field. It doesn't make a big difference. You could use one instantaneous temperature field, but the mean temperature field does the job. And when we can, we'll show how we use the impedances of the outlet and the inlet. And I'm going to be using active flames, what we call active flames. That means a non-zero flame transfer function. And sometimes it will be what we call inactive flame. That's just a temperature jump, but no active effect of the flame. So that's the equation which is solved by AVSP. It's an Helmholtz equation for pressure, which can be tricky to invert. The boundary conditions, that's the impedance that you need to specify. And here, you have the forcing due to the flame. Okay? So if you put a 0 here, and if you do simple impedances, codes like COMSOL, for example, do that. You can download that, and it will give you the modes. What they won't give you is what's happening if you put a flame there. But solving for the acoustic modes of a cavity is a usual problem. Okay, it's nothing special. What is special for us is that we have complex impedances and that we have a flame in addition. So the flame response we'll get from the flame transfer function. The sound speed, we can even get it from RANS, but since usually we do an LES, we also have it from LES. You can also guess it. In many cases, we just say it's cold and here it's burnt at equilibrium. That's sufficient for the precision you need. And the impedances, well, the impedances, as I said, that can be more tricky. I will give you examples. And remember also that if you do an LES, you're going to pay, hundreds, thousands of hours, maybe million hours. The acoustic codes is 3D, but it's very fast. It's going to be at least 500 to 1,000 times cheaper. So the DLR, I've shown this one during the seminar. That's the old Prekinstar burner, but that's a very good test case. If you write an LES code, this is really now the reference. Everyone is computing it just to make sure that it works. We've done it with Fluent, we've done it with CFX. OpenFOAM has been used too. So it's a swirl burner, premixed, and on this burner, this is the outlet, and this is the domain. Okay? So the atmosphere is meshed, and if you have an unstructured code, it costs you nothing. You put a few big meshes here, you get some refined zone here, and that's sufficient. And this way, you don't have to worry about the outlet impedance. There is one, but it's captured by the code. No problem. The inlet here is more tricky because we don't exactly know. A DLR told us there's about 10 meters line here. And so the inlet impedance is tough. Here we suppose that the flow rate was imposed. And that's the only two conditions you have: outlet pressure, inlet velocity, or atmosphere, flow rate, excuse me. So that's the mesh. And it's a non-structured mesh, just because to mesh the swirlers here with a structured mesh would take too much time. It would be too complicated. It's possible, just going to take a lot of time. Okay, so am I going forward or backward? Okay, I've said that already. This is the instantaneous field of pressure. You can start seeing the vortices here. And you see that, by the way, to come back to our discussion 2 days ago, this is at least an LES because it's moving. I've seen a computation with Fluent a few months ago, and nothing was moving. Then it's not an LES, okay? It's a RAN simulation. It has to move. If it does not move, it's not turbulent. If you average the results now, that's the averaged field. You find something which is not moving, it's an averaged, and this is what a RANS code would compute. Now, I've shown the comparison here 2 days ago. I'm not going to show them again. Just to come to this point here. This is the IMS azimuthal velocity, and it is very large here at the center of the domain. And you see the comparison again between LES and experiment is very good, so it's not an artifact. You have, at this point here, you have an IMS velocity of more than 15 meters per second. And if you look at the actual velocity is almost 0. So you have a very, very intense zone of turbulence with a very, very low mean speed. Why is that so? Well, it's the place where you get the PVC. Okay. The PVC, you can visualize it in the simulation. That's here you have the swirler. This is a low pressure zone. And if you visualize this low pressure zone, you see it's turning. You find the classical PVC. This is the animal making all the turbulence. This is why a RANS code cannot compute that, because this guy generates actually 95% of the activity. This is an isosurface of pressure, yeah? That's the same one. Maybe you have some problem seeing that. That's the blue zone here is also turning. It's also the center. It's the center of the PVC that is found by the low values of pressure. Now, by the way, since we are there, what would RANS give on this flow? We did a comparison with CFX at that time. The black line is AVBP and the red line is CFX. So you see that there are many places where the RANS code has problems. And you see, for example, also at the outlet that the diffusion leads to this kind of strange profiles for the RANS code. This is for the azimuthal velocity, now the rotation. The same thing. We know that K epsilon has problem with rotating flow fields, and you see it here. It's dissipating everything much too fast compared to the LES. But the worst problem is not that. You cannot compute U prime, V prime W prime is Fluent, but you can compute K. That's the plot of K. So K here, that's the symbols. K, this line is the LES, and you see that we capture it very well, which makes sense. We're capturing each component well, but you see where the RANS is. It's completely off by a factor of 100 or something like this, because it does not capture the PVC. And now it's a major problem, because remember that the field, the ratio K over epsilon, is the quantity that we will use for eddy breakup, EDC, all these models. So here, again, you see the weakness of RANS. Because the RANS model does not see this big eddy, it completely fails in capturing a good time. This time will be used for the turbulent combustion model, and you will get strange results. So I'm going back now to LES, and we start looking at unsteady activity. So DLR was doing the experiment, we are doing the simulation, and we are seeing a PVC. I've shown you this PVC, which was at 520 Hertz. So if we measure the frequency of rotation, it's 520. But then these guys in DLR, they told us they measured 300. So the student got nervous, and he said, well, be careful, where did you measure 300? This is the experimental spectrum. The point here was that they measured this signal in the plenum. So the experiment measurement was done here, and the LES, the signal was done here. So we said, okay, maybe you have 300, but in the chamber, you still have 500. So which is another message here. In the same chamber, you can have multiple frequencies at the same time. In that case, you have indeed the 300 Hertz here, but in the chamber it's a 520 when you look at the PVC. So what we did is that we asked them to put the microphone here, and that's what they got in the experiment. And indeed, in the experiment, there was this 500 Hertz mode. It's just that their sensor was not at the right place. So that was a nice thing to observe, that you can, with the LES, capture the same thing as you capture with the experiment. So that's for non-reacting cases. Then we ignited this thing. When you ignite these flames, they have this funny shape, you know, that if you make a cut through this flame, you have a shape like this. So if you visualize an isol contour, you get this funny shape that you see here, and of course it's moving because it's LES. And then you can start averaging these things and look at the results. So this is the actual velocity. Now this is with combustion. And you can see the type of quality that you obtained with LES here. You can try to do that with ones. So that's going to be interesting. Even the IMS velocity you capture, there are some peaks here that we don't see, but as you can see here, we really get most of the activity. And that was 10 years ago with a crude mesh. So it's really not a problem here with LES to capture. This is the azimuthal velocity. And again, you see the agreement's pretty good. And this is the IMS velocities of the azimuthal component. Now, is there an unsteady activity for this case? This is also where things get complicated. People do measurement in this thing. They see a frequency of oscillations for the cold flow. And then they say, when I ignite my flow, then I will find also unsteady activities. Well, not necessarily. In this case, you find indeed that there is a mode at 500 Hertz, but it's not, again, the fact that two frequencies are equal does not mean that the phenomena corresponding to these two phenomena are the same. This 500 Hertz mode looks indeed like the cold flow case, but it's not. How do we know? Well, the first thing we did is that we actually meshed the whole geometry here, and we computed the modes with the AVSP. So with the acoustic code, we can get the temperature profile. Here, we set P prime equals 0. Here, we set U prime equals 0, and we get the modes. And what we did then is this is the result we obtained. And then we compared to what LES was giving, and you see that the LES points in terms of P prime are right on the same curve. Here, they disagree a little bit. It makes sense because in the swirler, I think I talked to someone about that not long ago. In the swirler, you have acoustics, but you also have some pressure due to vorticity, to vortices. And you cannot separate what is acoustic and what is turbulent in this flow. This is why in the swirler here, there's some disagreement. But overall, clearly, we're really capturing the right mode. So it's an acoustic mode. So with combustion, if we see 500 Hertz mode, it's acoustic. It's not the PVC. Okay, let me go now to the second case, which is the Siemens burner again. That's old actually now. It's almost 10 years old. So the swirler, we've been computing many times, this chamber. And here too, there was an experiment done in Karlsruhe in Germany, and they measured many things on this thing. So this is the chamber. Of course, that's not the chamber of the real turbine. Okay, they keep one burner, they put it in a special chamber, and they do the measurements using optical access on both sides. So this is how the geometry looks like. So this is the combustion chamber. It's not choked, but there's a restriction at the outlet. And at the inlet, you plug one, only one. There are 24 in the real machines. Only one swirler of Siemens. These swirlers have a diagonal inlet and an actual swirler. So you inject air here and here. You inject fuel also at different places, here and here. So this thing makes all kinds of strange things. I'm going to go through them slowly. Here you have the pressure field, and here you can see the temperature. And that's the side view of the flame. You can see that obviously there's some interaction now between the pressure field and the shape of this flame. So the question was not to observe it. The question was to try to explain it. So the first thing we did is a non-reacting case. So this is a cut in the central plane. This is LES. You can see here the velocity components. And here you can see that's the pressure in one plane which is located here. When you do that, you recognize that you have a PVC again. You can see here the center of the PVC rotating. And you can actually visualize the PVC. And also what you have to do is to make sure that you're doing the right computation by comparing with experiment. So here the experiment is much more difficult. This is a big chamber, okay? This is a big animal. They cannot operate for a very long time. It's consuming a lot of gas. And so this is the comparison between the LES and the experiment at all these planes. And again, you can see that the mean actual velocities are pretty well captured. They were not able to do both sides, but since it's supposed to be symmetrical, that was not a problem. And this is again the IMS velocities. And you see that even here, in a complicated case like that, the IMS velocities are very reasonably captured. Remember also what I'm going to have to say again. When you do these things, you are comparing 5 average results from LES with experiments, whatever they are. And that may be a reason why sometimes you can have problems. For this case, it's a cold flow. When you do the reacting flow, it may be more difficult. So this is again now the swirling velocity, and I guess we have the IMS velocities. And you see that that was sufficient to go to combustion. So before we go to combustion, let me just show you the PVC here. That's the PVC without combustion. And you can see the rotation of this guy. It's a very strong one. And that's the one making noise. So this one is at 250 hertz before you ignite the flow. And again, you see that's a strange coincidence. But when you ignite this flow, it makes now noise and instabilities at 250. And again, there was a big discussion at Siemens saying, why is this a coincidence, or does it make sense that we would have the same frequency for the hot cases at the frequency of the cold case? And actually, again, we proved that there was no link between the two. It's just, again, a coincidence. So how do we know that? Well, again, here you cannot rely, on intuition. You need tools to do that. So how do you do it? Well, the first thing you do is that you do the computation with LES, with combustion. So you inject the air, you ignite this thing, you burn a few million CPU hours, and then you end up with this flow. So that's the result of the LES. And when we do that, we saw that the PVC was actually being damped with time. You see here it's disappearing slowly. And if you run it a little bit longer, it goes away. So the PVC at 250 hertz with cold flow goes away when it's hot. So he's not the problem. He's not the one generating the problem. That's another way of looking at the PVC. Here you can see it's turning, but then it's disappearing. It's going away. So it's not the instability that we see for the cold flow, which is the problem for the hot flow. Now the second proof is that you can run the Helmholtz solver, again, for the full geometry. And this is what the Helmholtz solver is telling you. It's telling you, okay, you get a mode here, 134 hertz, 250, etc. And here, you see there is 250. And so the mode number 2 given by the AVSP is matching the frequency of the experiment. So that suggests that what we see is really an acoustic mode and not something obtained because of the PVC for cold flow. Now, the surprising thing is that when we run the LES, we did not see it. The LES was not seeing this 250 hertz mode. And then again, you go back to the students and you ask them, well, why is it so? Well, it's interesting that when we did AVSP, we included the plenum in the system. And when you look at the mode, you see that this is unsteady pressure. The unsteady pressure is maximum in the plenum. So the 250 hertz mode is really a mode where the plenum is playing a big role. And the plenum is exactly what we removed when we did the LES here. This is the LES mesh. To save some time, we just removed the plenum. So it's not surprising that the LES did not capture the mode. You need the full system if you want to do that. So again, it's the kind of mistake you don't do when you use, but now we know you shouldn't do that. If you want to save money, it's not the right place to do it. So here the final result is no, there is no reason why the cold flow would influence the hot flow, and it's only acoustics There is no PVC there. It's the plenum here. So if you want to change something, you change the plenum. This is the place where things are generated. And this is what we presented to them at that time. Now, in the LES, there was still a mode. There was not 250, but there was another mode. And so this mode was also something we looked at. Unfortunately, they couldn't check it experimentally because it's a high frequency. That's the P prime that you obtain in the LES. So that's the pressure fluctuations. And you see it has a strange shape. You know, there's maxima in all corners. And if you visualize the pressure, this is what you obtain. And we have this discussion this morning again. So that's a very complicated thing. This thing is turning. And this thing is turning too. But this is acoustics. And this is convection. So the pressure field cannot be turning at the velocity of the swirl. But both are turning. And the existence of these modes here are somehow, we feel, of course, that there is a link between the two. But they cannot go at the same speed because one of them is going at the acoustic speed, the other one is going at the convection speed or something of this order. So we checked, the structure of this thing. We put probes in the azimuthal, in the longitudinal direction. As you can see, they are all in phase. So it's a mode which has no structure along the axial direction. But of course, it's a mode which has a structure along the azimuthal direction. All these probes are shifted by 90 degrees. So it's really a turning mode. So where does this mode come from? Well, you go back to the AVSP now again. And in AVSP, there is one mode here which has a frequency of 1200. Actually, there are two modes. One mode between these two walls, one mode between these two walls. Since the chamber is square, it's the same frequency. So these modes are again called degenerate because they have the same frequency. So you can combine them. Since they are the same frequency, you can add them with any phase you want. And this is what we did here. So this is the 1TX 1L mode and the 1TY 1L mode. These two modes can be combined in the AVSP. And this is an animation of what it would give. And you see that this is exactly what we observe in the LES. It's not LES here. It's purely acoustic. So you see that what this is telling us is that in the LES now, in this case, we have an additional mode, high-frequency mode, which is a transverse mode. And transverse modes are not a good idea in those systems. OK. Let me, well, we still have a few minutes here. Let me go to another case now, which is another European project called Fuel Chief, which was actually driven partly by Alstom this time. So it's a chamber where you have injection systems here feeding the plenum where it's swirled, and here you have the combustion chamber. Now this is the geometry. You can see here the premixed gases injected into this system, and this system feeds the plenum, and the plenum feeds the chamber. It's an interesting system because the acoustic boundary conditions are clear. Here, pressure is imposed, or almost imposed. And at the inlet, we impose the mass flow rate because they had nozzles. So in that case, it's rather simple. Now, when we're going to do the computation, what I'm going to show you is that we're going to change only one thing, the outlet boundary conditions. I'm going to go from conditions where this is completely non-reflecting. Any activity generated in the chamber will go out. And then I will change it to something which is P prime equals 0. In the experiment, they can't. To do a non-reflecting condition here, you would have to have a 10-meter long, at least 20 meters long duct so that there is no reflection. So to do it, you have to go into numerical methods which allow you to do that. So there's a sequence that we computed after a while to demonstrate what was going on. So we started by a non-reflecting outlet condition. Then we set it to reflecting during a few milliseconds here. And then we will set it back to non-reflecting. And you will see that when the outlet is non-reflecting, the flame is stable. When we close the outlet, it will become unstable. And then we open it, it will become stable again. So that's the objective of the exercise here. And during this exercise, we're going to use this energy equation, which I have shown. And we're going to do something which actually is difficult to do. we're going to close the budget of the acoustic energy. That means we're going to compute this quantity over the whole chamber. We're going to compute the fluxes at the inlet, the fluxes at the outlet, and we're going to compute this term. And that's something which is actually dangerous. We're going to try to see if this equation holds, okay? If the budget sums to 0, which is, that took a long time for the student. So that's the movie here. So when we start here, everything is open, the flame is stable. Then we close the outlet. You see the acoustic energy, that's the integral of the acoustic energy goes up. This flame starts oscillating very strongly. Then it reaches the limit cycle. Then we're going to open the outlet, and it will come back to stability. And it's in the computation, there's only one thing which changes, the outlet impedance. Everything else is exactly the same. Okay, now you see we go back to non-reflecting conditions, and the flame stabilizes itself. So that was a demonstration that in a simulation like that, the first order problem is what are the boundary conditions. And if you have the right boundary conditions at the inlet and the outlet, then you can have a stable or unstable case. Then you can do much more on this flame. What we saw here is that if we plot the total acoustic energy in the box, we see that it's growing. It goes to an overshoot, and then it goes to a limit cycle. And then when we open the acoustic boundary condition, it goes to 0. We can try to look at the budget now of the energy here. This is P prime, well, the integral of P prime, and the integral of the reaction rate. And you see that initially, you have a flame which is turbulent. There are fluctuations of pressure, the green curve. There are fluctuations of heat release, but basically they don't talk to each other. It's like as if everyone is living its own life. And then suddenly, one of them says, oh, you're going up, I'm going up too. Or you're going down, I'm going down too. Oh, you're going up, you're going down. Okay, let's do it. And then they start dancing together. Then you go into the unstable mode, and then, you know, the Rayleigh index, which was 0 here, is going up because pressure and heat release are in phase. Now you can plot here the balance of energy in the system as a function of the Rayleigh term and the losses. When you change the boundary condition, it's really the losses that you're changing, okay? And you see that these two terms, one of them is the red one, the other one is the green one, they match, which tells you that your simulation is consistent. You really close this equation the way you want. Now, since you close it reasonably well, you can start looking at the budget of individual terms now. So this is now the Rayleigh criterion in red, or the Rayleigh flux, if you want, and here is the losses. So when this guy is more than this one, you amplify. If this guy is less than that one, you damp. So initially, as I said, no one is really in phase. And then when the Rayleigh criterion starts increasing, you have losses also. And the more Rayleigh you have, the more losses you have. But still, at every instant, if you look at these curves, at every instant you have more gain than losses. So this is why this instability, you know, keeps going. And then here, that's an interesting part of the curve. Suddenly, at this point, you change that. You change the outlet impedance, and you see in 2 cycles, everything goes back to 0 because you have cut the loop, which means that there was a pressure wave coming here. For the instability to continue, it would have had to go back, but then you let it go out. And when it went out, it's finished. So just again, to remind you of what this really means, is that there is no such thing as a free burner. The burner depends on what's happening upstream and downstream of the combustion chamber. So you cannot guess what's happening to a given chamber by looking at the same chamber with different outlet and inlets. It's just impossible. I'm going to jump that actually because we have too many things to discuss today. Let me go directly to the last thing. One is also an Alstom burner, but that's a real one. And here we're going to talk about something else. We're going to talk about NOx, instabilities, heat transfer, and radiation. So that's a complicated story here. You know that quite often there's a simple way to stabilize a flame. You just put a pilot flame with a lot of gas, and the flame will become stable. But then the NOx will be not good at all. So there is a compromise to find between pollutant levels and instabilities. And systems like pollutants like NOx are very sensitive to that. So you need to find a way to keep the instability low and at the same time keep the NOx low. The NOx is an interesting animal. The NOx is produced by many paths, which I've shown 2 days ago. And it's really nonlinear. You increase temperature by 25 K, you multiply the NOx by 2 approximately. So which really means that if you have a mean value of temperature and you start having variations around it, they will not average. And we come back, as we did before, to the turbulent combustion problem. When you get low here, you don't do much less NOx, but when you get high, you do much more NOx. So the average of temperature oscillation on NOx is going to be very strong. So if there are fluctuations in your system, if you start having a temperature which fluctuates because of combustion instabilities, you're going to change the NOx emission by a large amount. So we need to compute the mean temperature and its IMS to do that. So if you want to do a good NOx computation there, you need a temperature field. To do that, you must have the good heat losses at the walls. You must also account for radiation. If it's not sooting, it's not too bad. But if the flame is sooting, then definitely you have to account for that. And you need also to be able to compute the instabilities, because this plus that will give you the pollutants. So what we did at that time, we did not have this analytically reduced chemistry, so we fitted a scheme. We knew that the chemistry would be lean, so we fitted a two-step scheme to the conditions of the gas turbines here. You can see it's a reasonably fast case. You have 100 meters per second for the methane air flames. And since we also wanted to do NOx, we did it with this global scheme methodology. We just said NOx is produced by N2 plus O2 gives 2NO. It's difficult to do less than that, okay? So now we have a 3 scheme for chemistry. That's sufficient to get the right flame speed and the right NOx emissions if you don't change too much the properties of the inlet gases. So for example, here, this is Guaimac, and this is the 3-step schemes for 0.4, 0.6, and 0.8. And you see that the agreement is quite good. This is the NOx, okay? So it's difficult to get. And again, it works because we do it only for 1 point of operation. 1 pressure, 1 temperature. And then you can do it. Today we would do it with analytically reduced chemistry. The other thing you need to do, and that's something we have not really touched here, but I know that if you do LES, you're going to have to worry about that. You need to do something with the lows, the wall lows. We don't have usually the resolution to go very close to the walls. So what we use is thermal and actually dynamic wall lows too. So the low of the wall is a way to avoid going too close to the wall. And we do that for the flow, and we do that for the heat transfer. And so you assume that the velocity profile is a log scale, and you assume that the temperature profile is a log function too. So this is coded in AVBP, and we tested it many times. This is, for example, in a channel like this, the Nusselt number as a function of the Reynolds number, and you see that this is the correlation, and this is the low of the wall, and that works reasonably well. Because we need to account now for this thing. We need to account also for radiation. So for radiation, you could spend your life working on that. There are good compromises here. One of them is this RADCAL program, where you just say that you have gray gases in your gas, and the emissivity here, the APK coefficient, is given by the concentration of these gases, the mass fractions. So it's only CO2 and H2O, which radiate. So you plug them here, and that gives you an idea of the flux lost by radiation. You don't know where it's going, okay? You just know it's going to TS, which is the infinitely, the temperature of the infinite medium. And that gives you an estimation of the flux, which is better than doing nothing. So when you do 1D flames like this, with radiation, temperature goes up, then it goes down, and the NOx goes up, but then it's less when you have radiation, okay? So you go from here to there. As soon as you add some heat loss, the NOx goes down. Okay? And that's the level of radiation which you expect. And again, you see that if you do tabulation will be here, and it will give you this amount of NOx, because tabulation won't have losses. Okay, now let me go to this burner. The EV7 burner of Alstom is the one I described this morning. It's a cone cut in two, and so the flow is turning like this here. And so here we inject methane here, and they also stage methane injection. They inject also methane here and there. So this way they can tune the regime, trying to make it stable if they have to change something. Now, the flame is here. The outlet is on the right side. And we're going to change the outlet condition, only the impedance, and we're going to change also the radiation model and the heat transfer model. So this is a view of this engine. It's a little bit complicated. When you inject methane here, you do it by multiple holes, and you inject it here too. So first, I want to show you what's happening when you do the case without any losses. So there is no radiation, and there is no cooling of the walls. When you do that, the first thing which happens is that the flame gets stabilized, but it's stabilized at the wrong place, let's say. You can see here the isocontours of methane, the 5 jets here, 5 jets on the top, and here you have the surface of temperature. And you see the flame is stabilized right away here at the lip, because since it's adiabatic, there is no reason for the flame not to come here and to be anchored on this surface here. In the real world, it cannot happen, because if it would, this point here would be at 2000 K, and it will melt. So we know that saying that the flow is adiabatic is a bad idea. But again, if you do a tabulated method, that's what you do implicitly. So then we went to a case where we included radiation and heat losses to the wall. And you will see that the topology of the flow now is completely different. So the cooling is included, and we have a non-reflecting outlet. So this is supposedly a stable case, as you will see now. So now you see the jets of methane, and you see the reaction rate, and you see now the flame is lifted here. It's not touching this point. It cannot, because this point is too cold. So the flame is still stabilized by the recirculating zone, but then that's also a question which was asked yesterday. That has become a V flame, while before it was a V flame, M flame, excuse me. If this is the injection here, now you have a V flame, and if you are adiabatic, the flame can come back here, and it becomes an M flame, okay? It's an M like this. So as soon as you add cooling, you go from M to V, and that's something actually which has been observed many times now in experiments. Now the interesting thing is that if you average those results, so you run the LES, you average everything, you start looking at temperature. You see that if you're adiabatic, you go to large temperatures here, and of course if you're not adiabatic, well, you go up and then you go down again because of radiation. But the effect of NOx on NOx is crazy. I mean, you get 30 ppm here of NOx at the outlet, and here you get only 3 ppm. So that makes a big difference. And to conclude, that will mean that modeling NOx here without modeling heat losses does not make sense. But unfortunately, if you look at instabilities, it's the same. What we did is we take this simulation and then we close the outlet boundary condition. So now the waves, the acoustic waves cannot leave. They are trapped here. So what's happening is, as you would expect, this thing starts oscillating, and it goes to a self-excited mode, which I've shown you before. It's this guy here. So this guy is very unsteady. You can see, the movement of the flame fronts. And again, if you average it now, this is what you find. If you have no unstable mode, you have this level of NOx, 3 ppm. But if you have instability, you have 7 ppm because of what I said when I started. If the flow is oscillating, temperature is oscillating, you do more NOx on average than if you're not oscillating. So again, that suggests here that if you want to model NOx in a consistent way, you need not only heat losses, you also need acoustic conditions, acoustic boundary conditions. So in conclusion, it really suggests that when you do all this computation of swirl flames, we should account for instability, heat losses, and radiation. Otherwise, we may be missing a big part of the problem. Okay, I'm going to stop here. If you have questions, that's the right time. Otherwise, we'll shorten a little bit the session today because it's Sunday, so you can relax. Can you repeat that, please?
What is the main reason
Where?
shifting the longitude mode to transfer mode within that few frequency range?
I'm not sure I understand the question. The main reason for what? For changing the outlet impedance?
No, what is the main reason
Yeah?
from shifting the longitudinal mode to the rotating mode, transfer in the gas turbine?
I don't get the question. So I'm sorry. Maybe I get tired.
Is asking what is the main reason
Yeah.
for shifting in the gas turbines you have shown, for shifting from a longitudinal mode to a transfer mode in such a small frequency region.
Well, shifting, it's not shifting. All these modes, all the modes are controlled by length, okay? So if you have an engine which is compact, this distance here is of the same order as this one. So the azimuthal modes are at the same frequency than the longitudinal modes. And that's what happens in most cases in gas turbines. So if you see a frequency, it can be a longitudinal mode or a transverse mode or an azimuthal mode. It's difficult to know as long as you don't have the structure. So if you know just the frequency and the frequency only, you're stuck. You need, or then you need more sensors. You need multiple microphones, but just the frequency is not enough. The physical reason now, why does the flame choose a longitudinal mode instead of a transverse mode? This has to be related to the Rayleigh criterion again. You need certain phase conditions so that the flame locks on one mode or another. And this is what, LES does it, and the acoustic modes do too. You have to include the flame transfer function.
Like we are trying to model this thermoacoustic instability using LES, not the acoustic solar.
Yeah.
LES we want to model. So it is relatively easy to get the right frequency. Like we have some experimental data, you're trying to mimic that. So you can get the frequency relatively easily.
Yeah.
But if you're trying to get the amplitude, it is much more difficult. Why is that so?
Well, the amplitude depends on a lot of things. Depends on the quality of the scheme, okay, of the numerical method. If the method is dissipative, you get less amplitude because it's damped. And also the amplitude very often in an experiment depends on things that you don't want to discuss. Leaks, for example. In my experiments, when I was doing my PhD, I had very small leaks, on the quartz window here. And if you have leaks in a region where P prime is large, then P prime is a little bit damped, and so in the experiment you get to another level. So it is what you say is absolutely true. Today we predict the frequency with very good precision. If you want to know the amplitude, I would say that if you get the amplitude within 30%, it's good, because it depends on many phenomena that. Also sometimes in the experiment there were liners that they didn't tell you there were liners, so the liners are damping also the whole thing. 20-30% accuracy should be expected, which is not that bad. No question?
While choosing the acoustic elements for, suppose we have a frame, you have assume that it's I think we generally don't have a 1D frame, right? For the jump conditions.
Yeah.
If we have arbitrary shape of frame, then how do we choose elements?
Well, if you want to know how to cut the system.
And then you cut it along the contours so that it eventually.
Well, there is some arbitrariness when you do that, of course, because in a real system, it's not really straight elements. What you have to do is you have a criterion which tells you, for example, when you mesh a nozzle like this, basically you cut it in one first piece here, then you have a second one here, etc. And this is approximate, of course, but it's basically a one-dimensional discretization of space. And you cut this thing and you say S1, S2, S3. And this is arbitrary, but in gas turbine companies, since they always use the same geometries, they know exactly how to discretize that. So for each geometry, they they know the length and the section.
In each section, see, suppose we have a 3 plane like this show.
Yeah.
So, I mean, even in very small, elements,
Yeah.
we want to have a completely 1D generation.
Okay. The flame is a problem. The flame normally should be compact, so it should fit in one element. So in other words, the flame should be like this, very flat. If it's not like this, if it's not a compact flame, and for Siemens quite often it's not, it's a long flame, then you need to have multiple flame elements, and each flame element will have its own flame transfer function, which gets much more complicated right away. But for Siemens, that's what's happening, because in a Siemens flame, the flames are very long, well, long, they're like this, and so you cannot assume that they are compact. So in that case, you need to subdivide the space into multiple flames, and that makes things more complicated. Yeah. But again, considering the cost of this thing, because it's very cheap, it's still a good deal. No other question? Okay, we're almost on time, so we'll stop here for today, and we meet again tomorrow at 9. Is that right? Okay, thank you.